Natural disasters are often interconnected and can occur as chain reactions. As climate change increases extreme weather events, communities face growing risks from these secondary disasters. In 2024 alone, the world experienced 393 natural disasters, causing over 16,000 deaths, affecting 167 million people, and resulting in over 350 billion pounds in damage. The challenge is not only predicting disasters, but also detecting where damage has occurred immediately after the impact. Our project addresses three Sustainable Development Goals: SDG 3, SDG 9, and SDG 11. Goal 3 focuses on reducing injuries and deaths caused by disasters. Goal 9 promotes innovation and resilient infrastructure. Goal 11 aims to make cities and communities more resilient. However, many current monitoring systems are expensive, complex, and difficult to deploy widely, which means many communities lack accessible ways to quickly detect disaster related damage.
Our solution is a low-cost impact detection sensor designed to detect sudden forces caused by disasters, such as landslides. The sensor is a box of non-Newtonian fluid with three conductive metal plates placed inside. When a sudden force is applied, the fluid stiffens and transfers the force to the plates, pushing them together and creating an electrical signal that indicates a dangerous impact. The key scientific principle behind our device is the behavior of non-Newtonian fluids.
Unlike normal liquids, which maintain a constant viscosity, non-Newtonian fluids change their viscosity depending on the force applied to them. Under gentle movement, the fluid flows like a liquid, but when a sudden force is applied, the particles inside the fluid temporarily lock together, causing it to behave more like a solid.
A common example is a mixture of cornstarch and water. In our sensor, three metal plates that are connected to an electrical circuit sit inside the non-Newtonian fluid. When there is no landslide, the fluid remains in a liquid state and the plates stay separated, only allowing a small current to pass through it.
When a landslide or sudden ground pressure occurs, the impact causes the fluid to rapidly stiffen and transfers the impact force into the metal plates. This pushes the plates together, creating a direct electrical contact, closing the circuit and triggering a signal that an impact has occurred. To evaluate this concept, we conducted several experiments. We tested different fluid thickness levels, examined how the sensor responded to various impact angles, and observed how the system behaved under different temperature conditions. We also performed repeated impact tests to study durability and reliability.
These experiments help us refine the design and better understand how the sensor responds to sudden forces. Because the fluid returns to liquid form after the force disappears, the sensor automatically resets and can be reused multiple times. This property allows the sensor to detect impacts from multiple directions and different force magnitudes, making it suitable for unpredictable natural hazards.
The materials used in our prototypes are inexpensive and are widely available. A working prototype can be built for approximately $20 to $30. Our sensor is reusable, reliable, and designed to withstand repeated impacts without breaking. Not only can we install this at construction sites that are prone to collapses, we can also install this in check dams and detect which part has been damaged and needs repair after a hurricane or flood.
Our innovation supports the UN Sustainable Development Goals 3, 9, and 11 by improving disaster response, infrastructure resilience, and community safety. First, good health and well-being. Our system helps emergency responders identify dangerous landslide zones faster, reducing injuries and potentially saving lives. Second, industry innovation and infrastructure. Our solution provides a simple, low-cost monitoring tool that helps improve infrastructure resilience in hazard-prone regions. By making disaster monitoring more affordable, our system improves recovery after cascading hazards.
In conclusion, by combining simple materials with fundamental physics, our innovation provides an affordable and scalable way to detect cascading disasters like landslides. With wider deployment, this technology could help communities strengthen disaster resilience and protect both lives and infrastructure in hazard prone regions.